There's a paradox at the heart of evolution. It's a paradox which calls into question the entire foundation of the modern synthesis of evolution, which is mutation and natural selection. When people think of evolution, they often imagine parents passing down their genetics to their offspring, with slight random modifications called mutations. Those mutations may be detrimental or beneficial, and selection weeds out the bad mutations and preserves the good ones. Over a long enough timescale, these mutations can build up and eventually you can turn a raccoon into a whale. This seems intuitive. After all, if creatures can change a little, and they can, then why can't they change a lot? Well, actually, it turns out there is a problem if you try to change things a lot, and it's pretty easy to see once you know where to look. In order to make it easy to see, I wrote up a simulation to visually demonstrate the paradox, instead of just talking about it. But before getting to that, let me set some groundwork first. Without getting too hung up on the technical details, the basic unit of genetics is the nucleotide. There's 4 of them, often denoted as A, C, G, and T, and these are kind of like letters in a sentence. A set of 3 nucleotides is called a codon, and these are similar to words in a sentence. Each codon codes for an amino acid, and long story short, they create a polypeptide chain of amino acids, which may or may not fold into a protein. And this protein is similar to a sentence, except if the sentence was really, really long. Proteins themselves are the fundamental building blocks of the cell and perform a lot of the functions that the cell needs in order to build and sustain itself. The final 2 things that you need to know is what a mutation is and what selection is. A mutation is when a nucleotide changes from one to another, and this can happen for a variety of reasons, but the point is that this change can affect the sequence of amino acids, which in turn may affect the protein itself. Selection is just a filtering mechanism. To put it simply, natural selection is just the process of decreasing traits which make it hard to live and increasing traits which make it easier to live. Of course, this is much more complicated in practice than what I laid out here, but if you can follow along with what I've said so far, then you know enough to understand the simulation. As an example, let's consider a protein that is under selection pressure. Maybe it's an enzyme that a bacteria uses to eat. Whatever it is, for the most part it doesn't really matter, as long as the protein is essential to the healthy functioning of the organism. The main thing that you need to know is there are a limited number of ways you can arrange nucleotides into amino acids in order to build a specific protein. If you tweak the nucleotides and change the amino acids too much, you will destroy the protein's function partially or completely. It's kind of like trying to rewrite a sentence by randomly changing letters here or there. It's going to tend to destroy the meaning of the sentence. Now, we know from recent research that proteins like this will be highly conserved, which just means that under pressure from natural selection, and in combination with mutations, proteins will tend not to change. And when changes do happen, they're going to be weeded out of the gene pool and replaced with proteins that have not experienced this change. In short, highly conserved proteins will still mutate, but they will still tend not to evolve because, well, then they wouldn't be highly conserved, but more specifically because selection will favor the most optimized and functional form of the protein. Now, if you're clever or an interested researcher, you might notice there's a potential way out of this problem. Perhaps you can remove selection pressure from the protein so it can mutate freely without the interference of natural selection. Maybe the protein is copied into a non-coding region through gene duplication or some other mechanism. It doesn't matter exactly what happens so long as the protein can mutate without being selected. So there you go, the problem's solved. Or is it? Well, it isn't, because we also know from recent research that protein folds are incredibly rare, on the order of 1 fold for every 10 to the 77 non-folds for amino acid sequences of length 150, which is a relatively short sequence of amino acids. Numbers like 10 to the 77 are almost impossible to imagine, so for reference, it might help to know that the Earth is estimated to be made of 10 to the 50 atoms. Now imagine picking an atom somewhere in the Earth and then being told to find another specific atom somewhere else in the Earth by randomly searching from one atom to the next without knowing where you're going. How long is that going to take to happen? Well, practically speaking, it's never going to happen. Even though this is many orders of magnitude easier than stumbling across a new protein by random search via mutations. When you have a system where ordered states are extremely rare and disordered states are extremely common, there's a word for how this system will evolve when random changes are made to it. It's called entropy. In this case, disordered or meaningless nucleotide sequences are far more common than ordered and meaningful protein sequences. So any random change to nucleotide sequences will tend to lead to disordered or meaningless nucleotide sequences. It's the same reason your Christmas lights get tangled and your room gets messy whenever energy is applied to them randomly. And the same reason tornadoes only destroy and never build. Now, if you're having a hard time following along, we can get to the simulation to help illustrate what I'm talking about. Let's take a look. When the simulation starts, you can see a model gene pool of 10 sentences composed of 4-letter words representing 10 copies of a protein. Similar to nucleotides, there are only 4 available letters, A, E, R, and T. And each of these can mutate from one to the other and back again. Every generation behind the scenes, each of the 10 sentences will produce 6 offspring, which will be an exact copy of the parent sentence, but they will have exactly 1 letter change, simulating a mutation. Spaces are ignored for the purpose of this simulation, they're just there for readability. After the offspring are generated, a selection algorithm is applied to all of the 6 offspring, and the most fit child, or the one most like the original sequence, will be chosen to replace the parent. If a mutation exists in the child, it will appear as a red letter. If you're colorblind, then look for the underline. With selection, you'll notice that the children don't stray very far from the original sequence, which means we've successfully simulated a highly conserved protein which resists mutation. In fact, in some generations, the chosen child sequence will completely revert back to its original form, free of any mutations, even though it previously mutated away from it. This demonstrates one of the strengths of mutation in natural selection. They are very good at optimizing the function of already existing genetic information. In other words, if you have a genetic sequence which is at least close to a well-functioning protein, mutations in selection are going to make it better. However, as I explained earlier, this is going to resist evolution as, in order to seek out new and unique proteins, you must fundamentally change existing proteins, which selection does not like to do. Okay, so that's all good so far, and hopefully you can see how a highly conserved protein will tend not to evolve. So let's be clever and remove natural selection in order to allow the protein to mutate freely in the gene pool. The protein sequence will no longer be highly conserved and might allow us to create something genuinely new. In a real organism, we might say the gene was duplicated into a non-coding region, or perhaps it just isn't as essential to the proper functioning of the organism as it used to be for some other reason. And so now selection will have a negligible effect or no effect at all. What do you think is going to happen? Probably see where this is going, but let's give it a shot anyway. As selection is removed, notice how rapidly every single sequence within the gene pool begins to become a random sequence of letters. In each of the 10 sentences, the sequence is virtually guaranteed to be almost entirely randomized compared to the original sequence. But why is this? Well, it's because of entropy. For a sentence of 36 letters, each with 4 possible values, that gives us a total of 4 to the 36 possible combinations of letters. It's like 4 sextillion, 722 quintillion, whatever. It's a really big number, and it's impossible to even imagine how big this number is. The number of possible combinations is roughly equivalent to about 10 to the 21, give or take. So when there is only one valid sequence for every 10 to the 21 invalid sequences, any random change to the sequence will naturally tend to find an invalid sequence. It's practically inevitable and cannot be avoided except through some directed mechanism that goes beyond mutation and selection. Now, you might say it's unfair to have only one valid sequence in the entire range of all possible sequences, but note that this is a simplified model, and it's many, many orders of magnitude more favorable than the estimated 1 in 10 to the 77 we find in real life. So I'm actually being extremely generous. In other words, my simulation is far more likely to find the one valid sequence of characters than a real organism is to find one truly novel protein by random mutation. But the other problem is, when dealing with numbers this large, it doesn't even really matter if I were to make 10,000 sequences out of the 10 to the 21 valid, because that's still only like 1 in 10 to the 17. So practically speaking, random changes just simply will not find valid sequences. Now, you can sit and watch these sentences evolve for as long as you like. They're never going to turn back to where they started by random chance alone. At least not in the time and resources that you have to watch. These random changes are not going to find a valid sentence in your lifetime or in many lifetimes, not even in millions or trillions of generations of sentences. And even if somehow you are lucky enough to see the simulation find the valid sequence again, the problem is it's just going to disappear as quickly as it did appear because there's no selection to conserve it. Finding a valid sequence while freely mutating would be like a blip of order in a sea of chaos, appearing and disappearing in the blink of an eye, especially on evolutionary timescales, or any timescale really. But let's say that by some unthinkable fortune, you are able to switch selection back on just within the very short window that the sequence becomes valid. The probability of this sequence of events happening has now just become orders of magnitude even more unlikely. But let's say that somehow it were to happen anyway by some miracle. Something like this doesn't need to happen just once. It needs to happen over and over thousands, perhaps hundreds of thousands or more times. And it only gets much, much worse from here because we haven't even touched on further coincidences like the metadata within genetics changing in just the right way at just the right time to put this protein right where and when it is needed in the organism, because by that point, we're talking about odds that are astronomical and possibly incalculably small. It simply won't happen, and it certainly won't happen as many times as life on Earth would have required if we all came from a common ancestor. Okay, so that was a lot to go over, but here's the rub. Evolving a short bit of information, like in the simulation, is one of the easiest tasks that evolution needs to accomplish, and as we've seen, it isn't even theoretically capable of doing that little bit. So, if the numbers don't add up, and if there is no plausible mechanism for it to function in the first place, then what exactly is the appeal to this theory? Even if it were true, evolution happens so slowly and over such long timescales that it isn't even relevant to us on a day-to-day basis. Evolution is like an interesting story or something that's interesting to imagine, but otherwise I see no compelling reason to accept it. So, if you are a Christian who believes evolution, then I have to ask, why? Are you actually following the evidence and reason, or is it something much simpler like peer pressure? Do you really know that evolution is true, or do you just not want to look bad? If you just want to see how it works, or you want to tinker with it and criticize it, you can find a link in the description to the simulation.